Okay, good morning. So I have, I guess, only two announcements. One is about the quiz that is coming today. The deadline is today. Please don't forget to do it. And then the tutorial today also, as I mentioned, I'll just, if there are any questions, I'll answer questions, and then if you want me, I can walk through the code. That's basically what's going to be for today's tutorial. Yeah. Okay. So if there are no other questions, let's get into the lecture. So we are almost done with address translation. Next step for us is to talk about caches and then how to make address translation faster, which is coming next. Okay, so the last topic, or I think the topic that we stopped on last time was on shared libraries. So in order to explain this, let me start with contrasting how you can code for shared libraries and how you can code for your, normal program. So if you remember, the whole point of virtual addresses was to take the burden off of compiler and the linker to think about virtual addresses. They could just use any virtual address they want to assign to any instruction they want. Now, what if you're coding for a shared library? What could go wrong if you use any virtual address you want, or if the compiler uses any virtual address they want? The problem with shared libraries is, as we explained, when you use in your code, when you have a printf, at some point, either at the beginning of executing your program, or in some cases right before you use printf, the shared library will be mapped to your virtual address. I think it would actually help if I use some drawing here. Okay, so I'm gonna make sure that you guys can see it this time. Yep, I can see that. You can see. Okay, so here is the idea. Let's say this is, making this closer to myself. Let's say this is program A. Or process A. And let's say that we map GCC, sorry, the libc library from address 0x. I'm just making it up. CFFF FF FF F to 0x DFFF. So this is, I'm just making it up. libc.so is, let's say, for process A, it's mapped into this address. So in physical memory, libcc is mapped somewhere. libc.so is somewhere, we don't know, from address X to address Y. It doesn't really matter. And then let's say there is another process that needs libc, let's say process B, and it just has happened that we mapped libc to address x b f f to c f f f. So this is completely possible, right? Again, as I said, during the runtime, you see, you find an empty region in the virtual address. So these are virtual addresses. So v address. So both of them are in virtual address space. So you find a hole in the virtual address space, and then you map libc. What do we mean by mapping? Basically, if I look at the page table of process B, I see that this region from BFF to CFF is translated to X and Y. And if I look at the page table of process A, I see that 0x CFF to 0x DFF is mapped to X and Y. So that's basically what I mean by mapping. Basically changing the page table to make sure that both of them, these two regions, are mapped to that physical region. Okay, so now what is the problem? So let's say you're the one who is coding for libc. Can you use any virtual address you want? Like, can you jump to any address that you want? Which is true, sort of, when you're writing your own program. You can have a jump, and that jump could go to any virtual address that you want, right? Well, the problem is you don't know who is running this code. Is it process B running it? Is it process A running it? Is it another process running it? You don't exactly know where in their virtual address space this library has been mapped. So that restricts you on the way you're using virtual addresses. So if there is a jump instruction in this library, in libc, this jump cannot use any virtual address. You can't say jump to address, let's say, 1FCB, blah, blah, blah. Why? Because you don't exactly know where this virtual address is mapped in the processes that are going to use libc.so. So this is actually not possible if you're writing a shared library. Instead, you have to use relative addresses for anything that you want to do. Let's say you want to jump to a specific instruction. Let's say the PC is here, pointing to address R, and you want to jump to R plus Q. So instead, you have to use a relative jump to say relative jump Q instruction from where you are right now. So that would be possible because that's basically address independent. It's just relative addresses. So that's the whole point that I wanted to make. That is the difference between writing a shared library, or not writing, but compiling and linking a shared library versus compiling and linking a usual program. Is basically that you cannot use any absolute address because you don't know where this library is going to be mapped. All you can do is to use relative addresses. Now let's go back to the slides. So now when it comes to shared libraries, we have two things to worry about. One is data, that shared library uses. One is the code. So the data cannot be shared because each process has to have its own data, right? Depending on their data, they're using the code. So we're going to use the code. So each process will have their copy of the data. But for the code, we can share. So we're going to share the code. Yeah, so the data, each process will have its own copies, and they would have read and write permission to their data. But then for the code, everybody will share it, and everybody will have only read and execute access. Now, as I just mentioned, you cannot use absolute addresses. You have to use position independent code, meaning that your code should be compiled and linked to be independent of where in the virtual memory it's going to be mapped, in which processes, virtual address range this library is going to be mapped. It should be independent of that. So the way it's actually done, yeah, I think I did. Yeah. So the way the yeah, okay. So do I have that last one? Yes. Okay. So the way it's done, so the way you make your code position independent. So now each code, as you remember, there might be two types of accesses to memory. One is instruction access, which is similar to that jump that I just gave you an example, jumping to an address. That would be a instruction reference. You could also have data reference, right? Let's say your shared library needs a global variable or whatever variable that it needs. So it wants to load that data, and that data has an address. Again, your code cannot use absolute address. It has to use relative address. Now, here is the part that is a little bit challenging. As I mentioned, each process is going to have its own data. And then everybody is going to share the code. So somehow we need to make data relative to the code so that from any instruction, you know how much you can go to find the data that you want. To fix this, we introduce a level of indirection. So what you do is you put a table at a specific address, let's say address 0 of your virtual of your shared library, assuming that wherever the PC is, if you go to the beginning of it, you get that data. So you can always calculate the relative address to the beginning of the code. And then in this table, you put all the variables that you have, all the data that you have, and then you keep the address of that variable or that data empty. Whenever the mapping happens, whenever a shared library is mapped to a process, you make a copy of this table and you fill the addresses with respect to the process that you have just mapped the shared library to, because now you know where those variables are. So you can put the addresses there. Now, every time the code wants a data, it has a relative address to the beginning of that table. It has a relative address to where that variable is. So all it needs to do is to check the actual virtual address there. So it's got just kind of a level of indirection to find the address that is used for this particular process. If now this shared library is mapped to another process, you make another copy of this table and you fill it with correct virtual addresses for this one, and then use it for that purpose. Now the same thing happens with instruction references. There is another table. It's called procedure linkage table instead of global offset table. So global offset table is used for data. The exact same concept, you use it for instruction references. So you put a table there, you go to that table, you figure out which, it has list of all the functions and all the labels that you can jump to. So you use that indirection to jump to relative addresses that you need to do. Okay, so that's that. Now let's have a discussion about multi-level address translation. So on the positive side, we were able to keep the memory usage for our page tables to bare minimum. So hopefully in ideal cases, the amount of memory that we use for page tables is proportional or is exactly relatively equal or approximately equal to the number of virtual pages that we're using that, the trick of using trees instead of a linked list, as I explained in the last lecture. We didn't compromise on memory allocation. We still have the memory paged, and that makes it easier to allocate and manage memory. It still allows us to share easily. We can do shares in the page granularity. We can share in super pages or segments, right? As we saw. So at each level you can share, and sharing at the last level means that you're sharing pages. Sharing at the first level means that you're sharing the entire address space, and sharing in between means that you're sharing different sizes of memory. Now, what are the downsides? One downside is, let's say in worst case scenario, let's say you have a process that uses all its virtual address space. It uses all of it. So in this case, it never happens, but let's say it happens. What is happening is that you have introduced all these middle nodes, all these if you're using, let's say, 4-level page table, you're now using only leaves, but then you had to also store page tables for the root and all its children, and that is basically now an overhead. You would have been better off if you just went with one big page table. And again, this doesn't happen, that a process uses in its entire virtual space, virtual memory. But let's say, hypothetically, if it happens, then you're introducing overhead. Okay, so as long as the process is using relatively a small portions of its virtual address space, you're saving. And if it uses the entire address space, you're introducing overhead, but that overhead is not that much, right? We're not talking about a lot of overhead. So it's relatively small, but nevertheless, we're introducing some overhead. So this actually talks about two-level. In two-level, let's say if you're using the entire virtual address space, then you're just introducing that level 1 page table. So that would be your overhead. The other thing to keep in mind is the page tables themselves are stored in memory, and the memory is paged, right? So we usually want to fit a page table in one page, because that makes it easier to read and write to that, because otherwise it's kind of hard. I don't want to get into it, but usually we try to fit them in one page. The other thing about it is that we also usually want to have all these pages for page table to be allocated in a contiguous memory region. Again, for performance related reasons. So there are again, without going further into details, there are some restrictions on where and how we can store the page table. I guess to just, you know, make it easy for you, as you will see, when it comes to page tables, the software is not usually the one walking through page tables, and it's usually the hardware that is walking through page tables. So as a result, we want to have a simple logic to traverse page table. All you want to do probably is to give hardware a pointer to the beginning of the page table and let the hardware traverse your page table. So again, that restriction, we'll talk about it later, but is basically what we need here. The most important downside, the most daunting downside of multi-level page table is you're accessing to translate one memory to do one memory translation. You're going through multiple memory accesses. So for one memory access, as I talked last time, as I said last time, you might need 5 memory accesses to just walk through your page table to do the translation, and that is super bad, and we have to fix it in one way or another. Okay, the last way of address translation is inverted page table that we're going to talk about. So in all the previous methods that we talked about, we had forward page table, and the size of the page table was large, as we saw, and it was very much related to the number of virtual addresses that you use. So in the naive way, just having page table, a big page table, you would have a big page table. In multi-level page table, you still could have a big page table if you're using a lot of your virtual address space. Now, with inverted page table, we want to fix this. We don't want to let the size of the page table grow. So we want to fix it. How do we fix it? We can actually use hash table to fix this. We can have the size of the hash table to be exactly the size of our physical memory. We use virtual address as key, and then we hash it to an address in physical memory, and then we just keep this hash table with us. The size of this hash table again is fixed. It's the size of your physical memory, and the key to this hash table is basically your virtual page number, and the value is basically the physical page number. Very simple idea. Now, it's not used that frequently in systems due to all the downsides that I'm going to actually talk about, but people increasingly are getting interested in these inverted hash tables as we are moving from a 64-bit system to 128-bit systems. So going to those bigger virtual addresses, we still cannot fully utilize the 64-bit, but when we do the transitioning to 128, then it's like it's huge, right? And we don't want to let the size of our page table also grow, and we want to fix it. So people are actually are paying a lot more attention to these and fixing their issues for the future systems that we might have, because this cap on the size is very appealing. But the problem with it is basically the problem with all hash tables. What do you do when you have an overlap? What happens if two virtual pages are mapped to the same physical page? What happens? So that's one, right? And we have to keep that in mind, that the one who is using this page table in most systems is the hardware, not the software. So whenever it comes to hardware, we want something simple, something fast, but there is already some complexity when you're talking about hash tables. How do you resolve that? It's an issue. I will talk in the next slide in more details. The other thing about it is that using hash table, usually you get not randomly, but each key could be assigned anywhere in the hash table, right? Now, what that means is if you have consecutive addresses, consecutive virtual addresses, there is a low probability that they would be mapped to consecutive physical addresses. Almost zero, right? It's kind of like in many settings, actually, hash tables are used to scatter something randomly between two in a range. So basically, each address comes in and then it maps somewhere in physical memory. Another address comes in, it maps to somewhere else pretty randomly. So if you have consecutive virtual addresses with high probability, they're not going to be consecutive in physical memory. And that is bad when it comes to caching, because when you're deciding what to cache and how to cache, you want to pay attention to data locality. So you're saying, if I'm reading this address, I'm probably going to read from addresses next to it. Now, this is true about your virtual address, right? Because your virtual address follows the routines of a program. So let's say it's an array and you're reading one address of your array. There is a high chance that you're going to read addresses around this address that you just read in your virtual address. Now, caches usually use physical address to cache memory, to cache data. Now you can see that this is not gonna help if you have a hash table, because if you read a particular physical address, even if the next virtual address that you're gonna read is consecutive, it might not be around this address. It might be somewhere completely different. So when you are caching, you don't have much locality information anymore, because it's just scattered all over your physical memory. So these are the two main pitfalls of inverted page tables. Here is an example. So as you can see now, the size of my page table at this particular time, I'm just having as many keys or as many entries as I'm using in my physical memory. If I end up using more bytes from my physical memory, I can just expand this hash table. But at most, this hash table will be having as many elements as my physical memory does. So the maximum size or maximum number of elements in my hash table will be the maximum number of pages in my physical memory. And all I'm doing to translate for any particular address, I just hash it using this hash table. So I use this virtual page number in red as key, and then hash it to find the corresponding translation to physical memory. So the total size of your page table is basically approximately equal to the number of physical pages that your program is using. It's a striking difference between this and all the forward translation methods in the past, where the size of page table was at best approximately the same number of virtual pages that the program uses, which could be a lot. Whereas physical pages, it's just limited. You have only certain capacity for your physical memory. Okay, so let's compare different ways of doing the translation. Now that we know methods of translating virtual to physical address, let's look at how we can implement them in our systems. So do we need hardware support for address translation? Like many other questions of this sort that I asked in the past, the answer is no. We really don't need hardware support. We can do it ourselves in software, but of course, it's going to be super expensive. So we would appreciate hardware support in address translation, because that could speed up the process dramatically. So that's one thing. Now, how do we implement page tables? There are two ways of implementing it. We can implement it in hardware, which is basically what you have right now in most of your systems, in x86 systems, in ARM processors, in Power, and so on and so forth. So the way it's done is that you put actually a memory management unit, a microcontroller, in your processor that would take care of this address translation, the whole ordeal. So this memory management unit needs to know a pointer to the page table. Now, whose job is to set this pointer? Obviously, the operating system. Every time you have a context switch, you have to also tell the memory management unit that the new page table is here. It's kind of like you take their hand, you put it on the new page table. You say, okay, now you have to deal with this page table. Previously, you were using this page table, right? So operating system gives instructions to this memory management unit, but that's all, right? When you start running your program, every time an address needs to be translated, the virtual address is sent from the CPU to the memory management unit, which is sitting next to CPU, and the memory management unit does the translation and brings the data back to the CPU, right? So it takes care of all the translation. Now, if memory management unit tries to translate something using the page table and the page is not valid, for example, or the permissions aren't set, let's say you want to write to a page that, according to the page table, you only have read access, then memory management unit tells the CPU that something went wrong, you have to raise exception. So CPU raises exception. At this point, operating system wakes up, takes control, and looks at the situation and decides what to do. So it could be that, as we talked about last time, it could be a stack is growing, so everything is fine. Operating system goes and changes the page table and tells the CPU re-execute that instruction that caused this problem. Or it could be that the program actually did something naughty and it didn't have, it was not supposed to do it. So we terminate the process with an error message of like segmentation fault or whatever. So that's the flow, which is basically very common in systems. The problem with it is that it's inflexible, right? You fix some mechanism for address translation in your processor and you implement it in hardware, and that is fixed forever. You cannot change that. Now, operating systems now need to know about this and adapt to this mechanism that this processor uses. So hopefully operating systems are flexible, so they can just, dance around the problem and bring some flexibility, but hardware implementation is fixed, nothing can be changed. But it's fast, right? Because everything is being done in hardware, so you can actually do this relatively fast. Now, the other way of doing this is to implement page tables in software. This gives you utmost flexibility. So what does that even mean? It means that for every instruction, hardware is going to trap to the operating system and say, translate this for me. Give the operating system an address and say, translate this for me. And then operating system runs some code to walk through its tables and data structures, whatever that operating system uses. It doesn't necessarily need to be the page tables that we talked about. It could use an inverted hash table. It could use anything it wants, right, to do the translation. And then once the translation is done, it tells the hardware, here is the address, now go to the memory. And as you can see, this is very flexible. The like you can implement any way you want, but it's super slow. For each translation, you're going to trap to the hardware, to the operating system, and then run some code to translate. So for every single instruction, you're just doing a lot of work, which is basically super bad, right? So no matter which one you choose, you need to speed it up. And the way to speed up things is by introducing caches, which is going to be the next lecture that we're going to talk about. So caching is the way around, because no matter which one you choose, software or hardware, you need to speed them up. And speeding it up is done by caches. So finally, this is basically the summary of all the things that we talked about. Different types of address translation I have excluded based on bound. So it starts with segmentation, page table translation, multi-level translation, and inverted page table. So the advantages of segmentation, we have fast context switching, and then the segment mapping is maintained by the CPU. With page table, we don't have any external fragmentation, and it's easy to allocate memory. With multi-level page table, we have decreased the size of our page table. It's fast and it's easy to allocate, similar to page table translation. And with inverted page table, the benefit was to basically cap the size of your page table to the number of physical pages that you're using. Now, the disadvantage of each one of them: with segmentation, you have external fragmentation. With page table, if you have large page table sizes, and if you want to fix that and have larger pages, then you would have internal fragmentation. With multi-level page table, the most daunting disadvantage is basically having to go through memory multiple times for each translation. And then for inverted page table, it's basically the complexity of the hash and also poor cache reuse. So hopefully that is a summary of all the things that we said during this lecture. Okay, let's move on to the next lecture. Okay. Okay, let's get started. So in this lecture, we're going to talk about principles of locality. We're going to talk a little bit about cache organization. I know some of you are taking the computer architecture course, and you have seen caching methods. But for those of you who haven't, this should be good enough. Then we'll talk about major categories of cache misses, and then we'll talk about how we can use cache to speed up address translation using translation look-ahead buffers. So basically, cache is a repository, right, that you use to copy the things that you are using very frequently to speed them up. So if there is something that you're frequently accessing, you want to cache them. So hopefully this repository is fast to access, and that speeds up your performance. It improves your performance because for those things that you are frequently accessing, you have a fast way of access. So that's the whole idea of cache. Caches are used pretty much everywhere in computer systems, from the hardware and multiprocessors and microcontrollers to big systems like clusters and data centers and all of that. So you can have a web cache. You can have any sorts of cache in your system to speed up the memory. So when caching is actually good? That's a question that you have to always ask. And to identify whether or not adding a cache would improve your performance. For a cache to improve your performance, you need to have frequent cases. So if you don't have frequent cases, let's say if you always are randomly accessing something, some address or some item, it's always random, there's no notion of locality, then caching introduces overhead. It won't speed up your system because there is no pattern in your accesses. So if you cache something that you accessed now, there is a low probability that you access that again because you're just randomly accessing things. So having that cache introduces, space probably overhead, and also checking that cache before going and checking the actual items would also introduce overhead. So previously you would just go to those items and check it. Now you are going through the cache, first checking if you have that item in your cache, and if not, you go back to your items, and that introduces overhead. So if you don't have any frequent access to a subset of items, then adding caches would not solve your problem, would in fact slow down your system and introduce costs. The other thing that is important is that your infrequent cases should be should not be too expensive. So if if there are items that are really infrequent, but they're so expensive, like very expensive, then those items will always, you know, be the deciding factor in your performance. Because even if you cache, even if you perfectly cache all your frequent items, those infrequent items that you're not going to cache are going to hurt your performance nevertheless. So so if that's the case, again, caching is not going to help you, because caching will speed up your frequent cases, but then you have those infrequent cases that are too expensive, right? And that becomes the deciding factor in your performance, and you always have them. So what's the point of having caches? Now, why do we bother introducing memory caches in our systems? Now let's focus on memory cache. So this is in this graph, in the x-axis I have time from 1980 to 2000, and on the y-axis I have the normalized performance growth. So this is basically the performance growth of a CPU. Almost, I mean, up to 2000, 2005, it was just going linearly up. But then this was the DRAM growth. This is the speed of memory. This is the growth of the memory speed over the years. So this was 2x every 10 years. This is 2x every 1.5 years. So there is a huge gap between CPU speed and DRAM speed. Now, as I talked to you about, for every instruction that your CPU wants to execute, you're going to at least go to memory once. So basically, memory becomes your bottleneck, right? If you're just going to go from your CPU to DRAM, your performance is going to suck, because for every instruction, you have to wait for your DRAM to come back. So basically, you're limited by the speed of your DRAM, not by the speed of your CPU. So that's basically the motivating factor to have caches. Now, when you have caches, what is the cache going to do? Cache is going to sit next to CPU, so it's on the same chip that the CPU is, so it's very fast. Now, instead of CPU going directly to memory, it's going to go first to the cache. And hopefully, if you have a good cache reuse and good cache mechanism, you can find your data in the cache, and that would eliminate the need for you to go to memory. So here, you basically eliminated the wait time for your DRAM by just introducing caches. But then the question is, how do we keep caches? How do we optimize caches, and how do we use caches to maximize the performance we can get out of them, which is basically what we're going to talk about. Now, so we saw why we should think about caches. Now, the other motivating factor that motivates us to use caches is because we actually have locality when it comes to memory accesses. So this is typically true for, like, this is an empirical observation. It's not like a rule or anything. Empirically, people observed that, let's say you have n bits to address memory. So there are 0 to 2 to n-1 different memory locations that you can access. People figured out that empirically you have these spikes in your and then on y-axis I have the probability of reference. So x-axis is the address, y-axis is basically the frequency, if you wish. So there are hotspots, basically hotspot addresses that you have frequent accesses. So what that means, what that tells you is, well, if I have these regions that I have a lot of accesses, if I can cache these addresses here, and wherever else they are, then I'm basically caching the addresses that my program is accessing a lot. And if I cache them, my program doesn't need to go to memory to find the data. It can just use the cache to access the data, and that speeds up my execution. There are two types of locality. One is temporal locality, one is a spatial locality. What you can see in this figure is basically a spatial locality, because it basically tells you if you're accessing one, if one address is hotspot, usually the addresses next to it are also hotspot. So that's a spatial locality. If you access one element of an array, you're likely to access the other addresses next to that element in the array. So that's special. With temporal locality, it means that if you access a particular location in memory, you're likely to access that same location in a window of time. So that also could happen. Let's say if you have a for loop and you're going through your array, so that gives you both spatial locality and temporal locality. Let's say you're going through your array multiple times. So if you go through one element now, there is a likelihood that you're going to come back to that element in future because you have a for loop, you have a while loop. Also, that would be temporal locality. So the same address that you access now, there's a likelihood that you would access that same address in future, very close future. You also have a spatial locality if you're going through the elements of your array. So if you're visiting element 0, there is a probability that you're in the next one, you're going to visit element 1, element 2, 3, and so on and so forth. So some terminologies when it comes to caches. The first one that is important, and we have sort of visited it back when we were talking about cache coherence, is the notion of block. So a block could be just one byte, usually not, but it's basically set of bytes, contiguous bytes in memory. We call them a block. So the typical size of block is 32 bytes or 64 byte or 128 bytes. You usually don't have blocks of 1 byte, but it could happen. So the granularity is just bytes, but usually the block size is much bigger than 1 byte. You want to group a bunch of bytes and call the entire thing a block. And that gives you sort of alignment, right, in your memory. If you have 8 bytes blocks, then you basically have 8-byte alignment. If you have 32 byte blocks, then you have 32-byte alignment, and so on and so forth. Now, hit means you go to cache for a particular item and you find it there. And hit time basically is the time that it takes you to go to cache and find your item. That miss is when you go to cache and you don't find your item in the cache. Now, miss time is a time to take the time that it takes to satisfy a miss. So these are different, right? So heat time is basically the time that it takes you to discover that you have the item, whereas miss time is the time that it takes you to resolve that miss. So you have already spent the time, heat time, to go to cache, and it wasn't there. So now you realize that your item is not there. Now miss time is the time that it takes you to now go to your memory and bring that data back. So to resolve this miss, we call it a miss time. Again, I want everybody to understand the difference. Because if it was just the time that it takes you to know that you don't have the item, it would be the same as the heat time, because basically heat time means going to cache and checking that item, right? Now, if you have it, that's heat time, you're done, you come home. If you don't have it, now your mission is to find it in your memory. So that's miss time. Everything after you realize that you don't have the item. Misses are usually expensive. They take longer time. So we want to avoid them. So we want to maximize our heat ratio. I guess I'll introduce heat ratio next. But we want to maximize the number of hits we get for each program. But then, nevertheless, they could happen, right? You could still have misses. So you want to really minimize the time it takes to resolve misses. Now, let's say you have a miss. So you couldn't find the data that you had in cache. So you have to go now to memory to find and bring that data. One of the ways that people do this to, again, minimize and amortize the miss time is to use those two things that I said, especially the spatial locality. Now that you know that you're accessing this particular memory address and you didn't have it in cache, it's very likely that you don't have also the addresses around it. And it's likely that you actually next time you're going to ask for another address, not exactly this address, but another address that is close by. So one thing you could do when you go to memory, so when a miss occurs, is for you not to just bring the byte that you were the block that you were interested in, but also some blocks around it. For exact same reason that I mentioned for spatial locality, because you might actually want them. Now this is a little bit tricky because your cache is usually small. So how much data should you bring? Should you just bring that byte, that block that you need? Should you bring that block and a block to the right and a block to the left? Or 2 blocks to the right, 2 blocks to the left? Or 3 blocks to the right, 3 blocks to the left? So that's a decision that you have to make. You have to realize that if you bring more data, it's called prefetching. So you prefetch, meaning that you're speculating that in future you're going to need those data. So you're prefetching them. Now, if you prefetch a lot, you're going to include your cache. So you're going to bring data to your cache speculatively, not exactly knowing that you definitely need them. If it ends up that you need them, good. But if it turns out that you really didn't need them, you basically wasted memory. You wasted bandwidth, memory bandwidth, and you also wasted cache capacity because you brought them and they occupied precious memory that could have been used for other data. So prefetching is actually an interesting topic in computer systems. How much prefetch, you know, whether or not to prefetch, and all of those questions. Those are interesting questions that you can ask. Okay, what time is it? Now, some more terminology. Heat rate means the number of hits you get divided by all the memory accesses that you have. So heat plus misses, that's total number of memory accesses. And heat ratio is basically the ratio of hits to all. Now, miss ratio is 1 minus heat rate, obviously. Now, what is average access time? So as I said, for every heat, you're gonna spend heat time. So heat rate times heat time. For every miss, you're spending heat time to realize that you didn't have it, and then you spend miss time to resolve it. So if you add this up, you get this. You always pay heat time, so heat time is always there, plus miss rate times miss time. So this is the formula we're going to use in this lecture for average access time. This is average because you have a rate here, miss rate and heat rate. So what's the problem now? If you stare at this equation, heat time plus miss rate times miss time, it has two components, heat time and then miss rate times miss time. Let's assume that miss time is out of our control. So if a miss happens, you have to go to memory and bring it. Let's say the time that it takes to go to memory and bring it is out of our control. Now we have two knobs to control, right? We can design our caches to have really good heat time. How do we do that? We'll talk about it in more details, but one easy way of doing it is just have a bigger cache. If you have a bigger cache, then it has more capacity, then you can cache more, then you can have, you can, oh, sorry. What I just described is a way to reduce miss rate. Apologies. So if you want to improve your miss rate or have a lower miss rate, if you want to miss less, have a bigger cache. Now, if you do that, if you have a bigger cache, then accessing your cache becomes painful. And the time to access your cache goes up. So your heat time goes up for your miss rate to come down. So usually what happens is you improve one of these two, you improve your heat time. To improve your heat time, you just shrink your cache. You have a smaller caches, you have better heat time. But you have a smaller caches, then you have higher miss rate. So one goes down, the other goes up. One goes down, the other goes up. So they're usually move in opposite directions. So that's basically the hard problem that we have to solve to find the sweet spot for both of them. Now, one of the ways that people have addressed this particular question is instead of just using one cache, you can use hierarchy of caches. And we'll see that how this could help us, right? Because you want to really have good heat rates, small caches, but you also want to improve your miss rate. You don't want to, if you miss in this very small cache, your next step shouldn't be going to your DRAM. You could have another cache, which is a slightly bigger, so which has more capacity. Now, this before going to memory. Now you missing this one, maybe you put another cache here. So basically put layers of cache to improve both of them so that you have really small caches for awesome heat rate, but you also have really low miss rate because even if you miss in this cache, there is a likelihood that you find your data in the next cache or the next cache before having to go to the memory. So you probably will find your data somewhere in your caches before you go to the memory. So kind of like addressing both of the issues by introducing more caches than just one. And this is basically what happens in current systems. So if you look at your processor, it has multiple cores. The fastest, fastest hardware to store data are the registers. These are really fast, but really small. Like in x86, you have only a handful of them. In your ARM processors, you have like 15 or 16 registers and so on and so forth. So they're not many, but they're very fast. After that, you have your level 1 cache. After that, you have level 2 cache. So level 1 and level 2 usually in modern processors are private caches, as we talked about in cache coherence. So these are two, in this figure, two private caches. And then you have a larger L3 cache that is shared by all the cores in your processor. And then after that, you have your main memory. Things don't stop there. You usually go to your secondary storage and your secondary storage and so on and so forth. So as you go this direction, you get larger spaces, but slower accesses. So in nanoseconds, this is approximate, but you have only few bytes here, hundreds of bytes, but then very fast access. The size grows this way, as does the access time. Usually registers are managed by the compiler, so they're sort of transparent to the programmer unless they're programming in assembly. Usually compiler decides which registers to use. So you just trust the compiler that uses the registers in an efficient way. Then you have L1, L2, and L3 caches. These are absolutely transparent to the programmer. So these are managed by the hardware, as we talked about when we were talking about cache coherence. Then you have the memory, the SSD, and your hard disk drive, and so on and so forth. The permanent storages afterwards. So these are usually managed by the software or operating system. So what we want basically is to make our accesses, memory accesses, as fast as L1 accesses. So we want to bring the access time as low as we could to anything close to L1 access time. So that's the goal. We obviously cannot exactly do that, but we can get very close. So that's precisely what we were going to do when it comes to memory translation as well, right? For those of you who are curious, I said in a multi-level cache, multi-level translation, for each translation you need 4 memory accesses. If you really were to go to your memory here, each instruction would require 400 seconds to be executed. And you obviously know that that's not the case in your systems. So that's how we're going to do it. We're going to make memory accesses super fast so that we rarely need to go to memory. We usually find our data in caches and we resolve it. In particular for memory translation, we're going to add another structure here, which you will see. It's called TLB, to cache precisely the memory translations. So address translations. We're going to cache address translations to speed up address translation. So just to do a little bit of interesting math, right? If you were to if you were given a system with let's say 4 levels of memory, you can think of it L1 cache, L2 cache, L3 cache, and then your main memory. Then one interesting thing is miss time at level 1. If you get a miss here, what's your miss time? Your miss time is going to M2 and coming back. So your miss time is basically the average access time at level X plus 1, right? So if I know the average access time here, I can calculate the missed time here, because missed time is basically going to M2 and coming back. And then if I know how much time it takes, then I know how much missed time it is in M1. So as a result, let's start with the CPU. What is the average access time of CPU? So it's basically the average, so it would be level 0. So average memory access time of level 0 is basically average access time of M1. Now, what is average access time of M1? It's based on that formula. It's the heat time of M1 plus miss ratio of M1 times miss time of M1. Now here I have the miss time of M1. I can use this equation here. So instead of miss time of M1, I put average time of M2. Now I can expand this, because now I know what is the average time of M2. Average time of M2 is heat time of M2 plus miss ratio of M2 times miss time of M2. Okay, again, I have a miss time M2. I can substitute miss time of M2 by average time of M3 and just keep going. Okay, now cache questions. Let's say, hopefully by this time I have motivated that we need to have caches, and caches are good. Let's say, okay, I've decided to have a cache. So I have my physical memory and I'm going to put a small cache here. Let's say, for the sake of argument, that each block is 1 byte. So I have all the bytes here in my memory. And let's say my cache is just an 8-byte cache. So it has only 8 bytes in it. That's the capacity. And my memory is a 32-byte memory. Now, let's assume that my CPU wants to access a particular memory location. So this is the address that I want to access in my physical memory. Now here comes the questions. Where to check in my cache to see if I have this memory? If this blue, whatever is saved here, how can I make sure that it's stored in cache? Which address should I check for this particular physical address? So basically, how do I know if this data is cached? Now that's one question that we're going to answer. The second question, let's say it wasn't cached and I have to go to it was a miss. Let's say magically I figured out it's not in my cache. I went to my memory, I brought the data. Now I want to put it in the cache. Where should I put it? Obviously, these two questions are related, because wherever we put it, next time we have to check it in that place. So where should I put this? That's another question. Lastly, let's say my cache gets full and I need to evict someone to make space for a new data that I want to cache. Which one of them should I evict? Which cache location do I need to evict for a new cache that I want to store? So these are the 3 main questions that we have to answer, which we'll try to answer in the coming slides. Again, some of the slides from here up to I think 5 or maybe 10 slides, you might have seen it in another course, in computer architecture course, but because not everybody is taking that course, as far as I know, it's an elective course. So I have it here for everyone. But for those of you who've seen it, it's gonna just be a reminder, hopefully. So the way we're gonna do this, I'm gonna actually finish this slide before ending this lecture. So, because I think I started a little bit late. So if you have to log off, do so, and then later on watch the end of the lecture. Okay, so we're going to divide the cache into disjoint sets of blocks. So each block in your cache is going to be a member of a particular set. and it's a one-to-one. So each set will have a particular, not one-to-one. So again, so each set has some blocks, and it's disjoint. So another set has another set of blocks, and these blocks are disjoint sets. So that's how we're going to create sets in our cache. Now, an M-way set associative cache. So this is a cache where each set has M blocks. That's what it means. So if I have two-way set associative cache, that means that each set is going to have 2 blocks. If I have 4-way set associative cache, that means that each set is going to have 4 blocks, and so on and so forth, right? Okay. Now, if I have a fully associative cache, this means that I only have one set, and this set contains all the blocks in my cache. That's fully associative cache. It gives us the most flexibility and longest access latency, as we will see how. So again, these two we'll see later on why. Another term here, a direct mapped cache is basically each set has only one block. So I think this covers the spectrum. So starting from the sets, these are disjoint divisions of blocks. Now, if you have M-way set associative cache, it means that each set has M blocks. If you have fully associative cache, it means that you have only one set that contains all the blocks. If you have a direct map cache, it means that each set has one block. So these two are the two extremes, and then M-way is something in between. Okay, now let's look at direct map cache and see how we can use direct map cache to answer the questions that we had before. So with direct map cache, each block belongs to a particular set. So there is a one-to-one mapping. So each set has one particular block. So I can finish this one and then finish the lecture. So each byte in physical memory will be cached to a single memory location, because now my cache has basically 8 blocks. Because it's direct map, each block belongs to a set. So I have 8 sets, right? Now I want each memory location is going to go to one set. Because each set is one block, this means that each memory location is mapped to a particular block in my cache. So I start from having to identify the sets in my cache, and then I map each memory location to one of those sets. So I have 8 sets, as many as 8 blocks, and now each memory has to be mapped to one of them. What does that mean? If you have 8 blocks and 32 bytes, and each byte has to go to one set, it means that you can just use the first 3 bits, basically, of your address to find that. So every 8, you have 32 and you have 8. Every 4 byte goes to one particular set. In this example, I look at the last 3 bits of my address, every time I get 1, 0, 0, I put it in 1, 0, 0 set here. So all of these would go to this particular set. So in this case, 4 memory bytes are going to one set, 4 other memory blocks are going to go to another set, 4 other going to another set, and I have 8 of them. 8 times 4, that's 32 bytes of my memory. So now we actually answered 2 questions, at least 2 first questions that I asked. So first one, if I have an address, how can I check if that exists in memory? Well, I can just yeah, I guess it's more than that. So to check if a particular address is cached, I can just look at the 3 last bits, find it in cache, but that's not enough because it could be any of these 4. It could be this one, it could be this one, it could be this one, or it could be this one. How do I realize which one I'm using? So I need to tag them. So what do I use for tag? I use the last 2 bits. So 3 bits I used for finding the location. I use the last 2, the remaining 2 bits to tag them. So I look at the tag. If the tag that I have stored for this location matches the last 2 bits, then it's a hit. And if it doesn't, it's a miss. So one question I answered, where do I cache a particular memory? I just look at the 3 bits to cache them. If I have an address, how do I check if that address is cached? I find that memory location, I look at the tag, and I check the tag with the address. And if if it is a hit, then I have it. And the last thing, how do I evict? Which byte should I evict? That answer is also pretty simple. You have to evict the memory location that the new cached address needs to go to, because each memory location is now mapped to a particular location. So if you want to bring a memory location, you only have 1 space for it. So whatever you already have in that space, you have to evict it to make a space for the new one. So that's the 3 questions for just the direct map cache. In next lecture, I actually talk about this in more systematic way, and I talk about all 3 types of caches: set associative caches, fully associative caches, and direct map caches. So this was just an example. We'll dive deeper into this. Okay, thank you for those of you who watched the lecture. Sorry I went over time. Talk to you this afternoon, and then see you next Tuesday. Take care, be safe, and bye-bye.